Hi everyone. So today we're going to start the new chapter, and that's finding the length of a curve. So we're going to start off with a quick little derivation of the formula, and then we're going to look at some examples. Okay, so imagine we've got the XY plane, like so, and we've got some function on the plane. Okay, so it can look something like this. Okay, so this function would be some function y of x. Okay, what we want to do is start at a point A and end at a point B, and then find the length of the curve between those points. So this length that I'm highlighting in blue. Okay, so how do we go about doing that? Well, the idea is that if we zoom in really close on the curve, then a small little segment might look something like this. Okay, if we look really close, we can approximate the curve by a straight line. In other words, at very short distances, the curve appears to be flat. Now, if it's flat, we can extend this to make a tiny little triangle. Okay, so we've got a little triangle here where along the horizontal, we've moved a little bit in the x direction. So let's call that delta x. And then along the vertical, we've moved a little bit in the y direction. Let's call that delta y. Okay, now, since these lines are perpendicular, we get ourselves a right angle triangle with a hypotenuse. Let's call that delta s. Now, we know from Pythagoras that delta s squared is equal to delta x squared plus delta y squared. Right, that's just our distance formula. Okay. Now, if we take the limit as these little triangles get smaller and smaller and smaller, then these delta s's and the delta x and the delta y, they turn into ds, dx, and dy, similar to in last year when you did your calculus and you found your derivative m, that was delta y over delta x. Then when you took the limit of very tiny steps, this became dy by dx. Okay, we're going to do the same thing here. We're going to look at the limits of very tiny steps. So these deltas become d's. So this becomes ds squared is equal to dx squared plus dy squared in the limit. In the limit of tiny steps. Okay. So what we want to do now is take the square root so that we can get the actual length of the hypotenuse. So we're going to have ds is equal to the square root of dx squared plus dy squared. So ds, that's the length of our tiny hypotenuse on the tiny triangle there. Okay, so this is the length, the tiny length of a very small triangle. So one of the triangles along this curve here. If we want the total length, we need to sum up all of the hypotenuses along the curve. But if we're taking the limit, then the sum becomes an integral. So the total length, that's going to be s, is going to be the integral from a to b of ds. So we're summing up all of the little lengths, but since we're taking the limit, the sum becomes an integral. So this becomes the integral from a to b, square root of dx squared plus dy squared. Okay, this looks a bit complicated because normally the dx is on the outside, but that's fine. We can manipulate this a little bit. So this becomes the integral from a to b, square root. What we can do is divide by dx squared and then multiply by dx squared. So we end up with dx over dx squared. Okay, plus dy by dx squared times dx squared. Okay, so we've just divided by dx and then times by dx squared, so we haven't really changed anything. However, the root of dx squared, we can take that out. So this is going to be the integral from a to b, square root dx by dx, that's just going to be 1, plus dy by dx squared. And then this root dx squared, that comes out to be just dx. So we get our formula to calculate the length of a curve. If the curve is given in terms of y of x, then we can find the derivative, substitute it into this formula, and then after integrating, we get the total length. Yeah, so this is going to be our arc length formula. Okay, so this is our arc length formula. Okay, so we use this formula if we have some function of x, so dy by dx. Okay, so that's our first formula that we need to know. Another formula is that if we're not given the curve as y is a function of x, instead we are given a parameterized curve. So for 2, we're dealing with parameterized curves. Okay, so these curves are not like y is a function of x. Now, both x and y are functions of some other parameter called t. So we're given x of t, y of t, where t runs over some range. So let's say 0 to 1. So for each value of t, we get a point on the curve. And if we go over the interval, we get all the points along the curve. So each value of t gives a point on the curve. In this case, we substitute t and we get an xy point. Okay, if we substitute t equals 0, then we get the start of the curve, because that's the start of our interval. So it gives the starting point of the curve. When t equals 1, that gives the ending point of the curve. Okay. And any other value of t will give some point in between. So other values of t, okay, from 0 to 1, give the in-between points. On the curve. Okay. So for example, let's say x of t is equal to cos 2 pi t. Y of t is equal to sin 2 pi t, like that. And let's say t goes from 0 to 1. Okay, so what kind of curve does this give us? Well, notice that x is given by cos and y is given by sin. So notice x squared plus y squared is equal to, if we substitute, we get cos squared 2 pi t plus sine squared 2 pi t. But remember, it doesn't matter what the argument is. Cos squared plus sine squared, these arguments are the same. So this gives us 1. So we have a circle of radius 1. Okay, which is good. And if t is equal to 0, then that gives us our starting angle of 0. And if t is equal to 1, this gives us an angle of 2 pi. In other words, we go all the way around the circle. Okay, so in this case, we can do a little sketch. So let's fix that. So here, this would be t equals 0, because that's the start of the circle. This would be t equals 1/4, because we're 1/4 the way around. And then as we increase t, we get back to the beginning when t is equal to 2 pi. So substituting different values of t give us all the points going around the circle. Okay. And then another, well, let's leave this for homework. You can sketch this one. So sketch the curve given by x of t equals 2t plus 1, y of t is equal to t minus 2. Okay, so if x is given by this parameterized form and y is given by this parameterized form, what does the full curve look like? Okay, going from 0 to 1. Okay, that should help you figure out how you draw these curves. Okay, so that's a little introduction on parameterized curves. How do we find the lengths of them? Okay, so finding the lengths of these parameterized curves. Okay, so we start off with what we had before with that ds squared. So the total length will be the integral. Now in this case, we're integrating over t. So t goes from 0 to 1. And then we had the square root of dx squared plus dy squared. Remember, that was our ds that we had earlier. But now x is a function of t. So since x is a function of t, then dx is going to be dx by dt dt. And y is a function of t. So dy is going to be dy by dt dt. Okay, because both are functions of t now. So let's substitute that in. So this will be the integral from 0 to 1, square root of dx becomes dx by dt squared, dt squared, plus dy becomes dy by dt squared, dt squared. Now this dt squared we can take out. So this becomes the integral from 0 to 1, square root of dx by dt squared, plus dy by dt squared, dt. Okay, and this is our second arc length formula, but this time with a t parameterized curve. Yeah, so we've got two arc length formulae. So 1 is if we have y as a function of x, and we've got this one over here if it is a parameterized curve. Okay, so that's our second formula. Okay, so let's have a look at some examples of using these two formulae. Okay, so example 1. Okay, so we're given the following curve. Y is equal to x to the 3 over 2. Okay, and we want to find the length of this curve from 1 to 4. So from x equals 1 to x equals 4. Okay, so to find the length, we need to first find the derivative. So dy by dx is going to be 3 over 2 x to the 1/2. Okay, and then we need to square this. So dy by dx squared will be 9 over 4x. Okay, so now we can use the first arc length formula. So the length S is going to be the integral from 1 to 4, because x goes from 1 to 4, square root of 1 plus dy by dx squared dx. Okay, and we've got all the pieces we need now. So this is going to be the integral from 1 to 4, square root of 1 plus 9 over 4x dx. Okay. Now you can either just integrate this directly if you know how to do that, or we can do a u substitution to make this simpler. Okay, so let's do a u substitution. So u is equal to 1 plus 9 over 4x. So du will be 9 over 4 dx. In other words, 4 over 9 du will be our dx. Okay, so that's the substitution. Remember, we also need to change the bounds. So if x is equal to 1, then u is going to be 1 plus 9 over 4. Okay, that's going to be 13 over 4. If x is equal to 4, that's the upper bound we've got here, then u is equal to 1 plus 9, that's going to be 10. Okay, so we've got the new bounds and the new integrand. So that's going to be the integral from 13 over 4 to 10. And then we have the square root of 1 plus 9 over 4x, that's the square root of u, times 4 over 9 du. Okay, so we can take that out. So we have 4 over 9, integral from 13 over 4 to 10, u to the 1/2 du. Okay, so same as always, you add 1 to the exponent to make it 3 over 2, divide by that, so we get 2 over 3 times 4 over 9, then u to the 3 over 2, from 13 over 4 to 10. Okay, so this gives us 8 over 27, 10 to the 3 over 2, minus 13 over 4 to the 3 over 2. Okay, so that's going to be the length of the curve. Okay, are there any questions about this example? Okay, let's put another homework problem. Okay, so find the length of the parabola, okay, y squared equals x, from 0, 0 to 1, 1. Okay. So it's a sideways parabola because it's y squared equals x. So we want to go from the origin to this point. I want to know what the length of that little segment is. Okay, someone wants me to re-explain. Which part? The integration? The integration steps. Do you want me to go over again? Okay, so let's do the integral again. Okay, so we have S is the integral from 1 to 4, square root of 1 plus 9 over 4x. Okay, so we need to do a u substitution first. So u is equal to 1 plus 9 over 4x. Okay, now we need to find du. So du is going to be du by dx dx. So du will be 9 over 4 dx. Okay, but we just want dx by itself. So we need to take the 9 over 4 to the other side. So we get 4 over 9 du is equal to dx. Okay, so we've got our differential now. Now we need to find the new bounds. Okay, so the old lower bound was x equals 1. So the new lower bound will be u is equal to 1 plus 9 over 4 times 1. Okay, because x is equal to 1. So that's going to be 1 plus 9 over 4. We can write that as 4 over 4 plus 9 over 4. So 9 plus 4, that's going to be 13 over 4. Okay, so that's going to be our new lower bound for the integral. Okay, what about the upper bound? The old upper bound was x equals 4. The new upper bound is going to be u is equal to 1 plus 9 over 4 times 4 because x is equal to 4. So u is going to be 1 plus 9 because the 4's cancel. So u is going to be 10. Okay, that's the new upper bound. So let's substitute that in. So this is going to be the integral from the new lower bound. That's going to be 13 over 4. Okay, we work that out over here. The new upper bound, that's going to be 10. We work that out over there. Okay, 1 plus 9 over 4x, that's going to be replaced by u. Okay, because u equals 1 plus 9 over 4x. So that becomes root u times dx is equal to 4 over 9 du. That's from this step over here. So that's going to be 4 over 9 du. Now 4 over 9 is a constant, so we can take that outside the integral. So that's going to be 4 over 9. The integral from 13 over 4 to 10. Okay, and then root u we can replace with u to the 1/2. Okay, if you have root u, you can replace it with the exponent form, which makes it easier to use the power rule, du. Okay, so that's going to be 4 over 9. Now, if we're integrating u to the 1/2, remember we need to add 1 to the exponent. So that becomes u to the 1/2 plus 1. Okay, so that gives us u to the 3/2. Then we need to divide by that, so we get 2/3 in the front. Okay, so that's going to be times 2/3 u to the 3/2 from 13/4 up to 10. Okay, now we can multiply the fractions in front. So 4 times 2, that's going to be 8. 9 times 3, that's going to be 27. Then we need to substitute the upper bound. So we substitute in 10. So it's going to be 10, it's going to be 10 to the 3/2 minus, we substitute the lower bound. So that's going to be minus 13/4 to the 3/2. Okay, and then that's our answer for the length. Okay, is that all right? Okay, let's take a look at using the other formula. Okay, so given the parameterized curve, okay, so it's going to be x of t is going to be cos par times t, and y of t is going to be sine par t, where t goes from 0 to 1. Okay, so we've got this parameterized curve. We want to find the length from t equals 0 to t equals 1. Okay, so we need to find the derivatives and then substitute that into the formula. So the first thing we need is dx by dt. Okay, if we take the derivative, we're going to get minus par sine par t. Okay, and then we want to square this. So we get dx by dt squared is going to be par squared sine squared par t. Okay, then we need to find the y derivative. So dy by dt is going to be par times cos par t. And then we need to square it. So dy by dt squared is going to be par squared cos squared par times t. Okay, then we substitute that into our formula. So we want the length, let's call that s. It's going to be the integral where t goes from 0 to 1. Then it's the square root of dx by dt squared plus dy by dt squared dt. Okay, so let's substitute the two things that we know here. So that's going to be the integral from 0 to 1, square root of dx by dt squared. That's going to be par squared sine squared par times t, plus dy by dt squared. That's going to be par squared cos squared par times t, and integrating with respect to t. Now inside the root, we can factor out the par squared. So that's going to be the integral from 0 to 1, square root par squared sine squared par times t plus cos squared pi times t dt. Okay, now sine squared plus cos squared, that's going to give us 1. Okay, so all of that will give us 1. So this will be the integral from 0 to 1. The square root of pi squared, that's just going to be pi dt. Okay, now we can take the pi outside. We're going to get pi integral from 0 to 1 dt, but that's just going to be 1. So we end up with just pi. Okay, now that makes sense because if we look at the parametrization, we see that it's a semicircle. Because if we just do a little sketch here, when t is equal to 0, we're over here. Okay, so this is our start. When t equals 1, we're over here. That's the end. And we're moving along like this. Okay, so we have half a circle of radius 1. Okay, so the full circumference would be 2 pi r. Okay, so in this case with radius 1 would just be 2 pi, but we're only going around half the circle. So the distance of the semicircle here is just going to be pi. Okay, so that distance is just pi, or you can say pi units. Okay, any questions on that? Okay, no questions with that. Okay, so let's take a look at some homework problems. Okay, I've got a few here for us to do. So number 1, we have y is equal to 1 plus 6x to the 3 over 2, where x goes from 0 to 1. Okay, number 2, y is equal to the natural log of cos x. Okay, and that goes from 0 to pi over 3. Okay, and number 3, we have y is equal to the natural log of 1 minus x squared. And x goes from 0 to half. Okay, and last one, y is equal to 1 minus e to the minus x, and x goes from 0 to 2. Okay, so a couple homework problems just to practice out. Practice using that first integral formula. Okay, any questions on these? Okay, so I'll post these on the WhatsApp group so that you can see them over there. I'm still waiting for more solutions from yesterday's homework problems. So I'll wait for those to be posted and then I can award your bonus marks for that. I think someone only posted a few of those. Okay, so then you can do these problems here for some more bonus marks. And then if no one has posted any solutions, then I'll post the solutions for both yesterday and today's problems. Okay. Remember, tomorrow is the summative quiz on trig substitution and partial fractions. Okay, then on Thursday and Friday, we will carry on with these arc length formulae questions. Okay, I'll see all of you then. And if you do have any questions, please email me or post on the WhatsApp group. Yeah, bye everyone.